Hello class, today we're going to go over Unit 8, lesson number 1, and that's 8.1, exploring the logarithmic function. So we're basically going to figure out what the log graph looks like, how it relates to another function, and what that log button does on your calculator. Alright, so we know that the inverse of a function is the reverse of its coordinates. So if I asked you to find the inverse of a function, which is what we went over Unit 1, and I asked you to find it algebraically, we would do that by switching the x and y variables and solving for y. Okay, so for this quadratic here, we have y equals x plus 3 squared. So we would switch the x and y as I did there in green. Okay. And then to get y on its own, right now it's trapped in the y plus 3 all squared. So we take the square root of both sides, considering the plus or minus. Then we would have to get rid of this plus 3 with the y, so we'd subtract 3 from both sides, and we would get plus or minus root x minus 3 equals y. Okay, and notice that I am not using this notation. Okay, that is inverse function notation when you use this part here. We cannot use that here because the inverse is not a function. Okay, we can see that this fails the VLT. All right, how do we find this graphically? So to find the inverse of a function graphically, you always reflect the function in the line y equals x. So that's this line here in purple. Okay, so that's the line y equals x. So visually you might be able to do that. If you want to obviously get more exact points, you can just interchange the coordinates for the point of the original function. So you can start with your parent function here. It's 5 key points. -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, which we can see in blue. It's an opening up parabola. And if I wanted the inverse, all I'd have to do is swap these. So we get the point 4, -2, 1, -1, 0, 0, 1, 1, and 4, 2. And that would create this graph here. So you can see that when the parabola opens up, its inverse opens to the right. So the whole point of going over inverse functions again is because it's going to pertain to today's lesson about log functions. So I just want to remind you how we go about it algebraically and graphically, because we're going to continue to do that with something else today. So, question, what does the graph of the inverse, right, of an exponential function look like? Okay, so the inverse of an exponential function, and we are going to work with y equals 2 to the x. We typically always work with that parent function, but obviously in this case here, this is unique, okay, because the b value here is greater than 1, right? So we know that this is going to be exponential growth based on the fact that the base is greater than 1. Okay, so I already know that the graph should look like it's growing. Okay. All right, so let's figure out what the inverse of this looks like. So you can start with your table of values, -3 to 3. Okay, and you shouldn't need your calculator to do many of these because we can use our exponent rules. So if I plug in -3 here, I'm going to get 2 to the -3. And using exponent rules, we always get rid of the negative by bringing the whole power down to the bottom and making the exponent positive. So this equals 1 over 2 to the 3, and that's about 0.125. 2 to the -2, same process, do 1 over 2 to the 2. That's 1 over 4, so that's 0.25. 2 to the -1 is 1 over 2 to the 1, which is just 1/2, so 0.5. 2 to the 0 is 1. Anything to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4, and 2 to the 3 is 8. All right, so at the side here, if you'd like, you can write out then what's the table of values for the inverse. Okay, so you're just going to swap the x and y values that you had here. All right, so now you have x as 0.125, y is -3, and so forth. All right, I want you to graph both of these on a grid. So graph both of them. Keep in mind here as well what type of asymptote do we have for exponential? We always have a horizontal asymptote. Okay, so this one hasn't been transformed up or down in any way, so the horizontal asymptote is at y equals 0. All right, so this is what their graph should look like. So there's our horizontal asymptote, okay? And it starts off right, the larger the negative value, the closer it is to that x-axis, right? And then we start moving upwards, we cross the y-intercept at 1, and then we go, and then we increase steeply from there, going through all the points. So that's the shape of y equals 2 to the x. Now remember, the inverse is a reflection across the line y equals x. Okay. Just so you can kind of visually see the mirror image here across this line. If you go ahead and plot all these points here in red, this is the graph that you're going to get. And we can see that definitely looks like the mirror image across that line. So what happens here is that this part here that's getting close and close and close to that horizontal asymptote has now been reflected to do that same pattern here, but now it's getting close and close to the y-axis, which is essentially x equals 0. So we just found out that the horizontal asymptote becomes the vertical asymptote of the inverse. Okay, so it switches. So we just found here that this guy has a vertical asymptote at x equals 0. Okay, that vertical line. And that makes sense, right? Because the x and y's are supposed to switch with an inverse, so that makes sense. All right, so we can see here the blue graph was increasing, and its inverse is also increasing, but obviously has a completely different shape. Okay, so what was the domain and range of the exponential function? So the exponential function here has a domain of xer, and it has a range that is restricted. It's yer such that y must be greater than 0. Okay, so notice you don't put the equal to because of the horizontal asymptote. Okay. That answers part D. Does it have a vertical or horizontal asymptote? It has one at y equals 0. Okay, we already did part E. We already graphed the inverse. So now let's discuss the inverse. Is the inverse of the exponential function a function? So we're going to go back. If you look at the red graph, does it pass the vertical line test? Yes, it does, right? It might look like it's a vertical line here, but it's not. It's just getting closer and closer to that vertical asymptote. So yes, it passes the VLT. What is the domain and range of the inverse of the exponential function? So if we go to the inverse, the domain has now been restricted because now you can only have x values greater than 0. And now because this arm's going to keep expanding and this arm's going to keep going down, the range is now yer. And remember, that makes sense based on our rules from Unit 1, right? That tells us that the domain and range should swap for the original and the inverse. Okay. So it makes sense that the domain of the original became the range restrictions of the inverse, and the same for range. Does the inverse have a vertical or horizontal asymptote? We just saw it has a vertical asymptote at x equals 0. Okay, now we are going to graph. Okay, so now we're going to graph the exponential function y equals 1/2 to the x and its inverse on the same axes. Okay, so notice now, okay, that we have changed the b value to be between 0 and 1. Okay, so let me just fix there. So the b value is between 0 and 1. Okay, so therefore this should represent exponential decay. All right, so when we do 1/2, let's create a table of values here to graph. So 1/2 to the -3, that's 1 over 2 to the -3, and then to get rid of that negative exponent, you bring it up to the top, so 2 to the 3, which equals 8. 1 over 2 all to the -2 means the -2 goes to the top and bottom. 1 to anything is going to be 1. So that's 1 over 2 to the -2, bring it up, become positive, so that's 4. You're going to continue with that pattern with exponent rules. And what you should notice is that you get all those same y values that you got with y equals 2 to the x. However, you're getting those y values for different x values, right? It's a bit reversed now. And that makes sense because now it's decreasing instead of increasing. All right, you're going to take those points and swap them to find the inverse. And your graph will look like this. And notice this looks much different than the first example we did when the base was 2. So we can see here, here's the line y equals x. We've got our parent function here, y equals 1/2 to the x, decreasing, having a horizontal asymptote about y equals 0. And if I were to take the mirror image of this and swap the points, it would create this graph. So notice that we've got, it was a decreasing function here, and now it's also a decreasing function as its inverse, okay? But definitely looks a little different, and now we've got that vertical asymptote here. So is the inverse of this exponential function a function? Okay, so yes, we can see here that it does pass the VLT. What is the domain and range of the inverse of the exponential function? So the domain of the, the domain and range of the inverse of the exponential function. So we can see here that x must be greater than 0 because it cannot pass over here into the negatives, and it cannot equal 0. So x must be greater than 0. And because this arm's going to keep going up and this arm's going to extend downwards, that means the range is YER. And just like with the previous example, the inverse of the exponential function had the vertical asymptote x equals 0. So it has a lot of the same characteristics as the previous example. However, you can see that the graph definitely looks different. All right, so in summary, what have we realized here? We have figured out what the inverse of exponential functions look like, okay? And that is an introduction to log. So the inverse of an exponential function, y equals a to the x, okay, or b to the x, okay, you can use a or b, is the log function. Okay, so what is log? That's the big mystery here that we have just solved. So the log function is the inverse of the exponential function y equals a to the x. Okay, so if that's the case, then the inverse of the exponential function y equals a to the x can be written in two ways. So this is the way we're used to. We're used to where we just swap the x and y coordinates, the values here, so replace here, so we get x equals a to the y. Okay, this is what we call the exponential form of the inverse. Right, it still looks exponential. So in math, what we've decided is that we've decided to actually call this inverse equation something else. So instead of writing it like this, which can sometimes look a little ugly because we always in math like to have y equals. So we decided, okay, let's rewrite this in a different way and call it log. So this is the same thing as this, and it says y equals log, and now that little a there is the subscript. Okay, so it's the base of here becomes the base of log is what we say, and then x up top. So this is the log form of the inverse. Okay. So these two things mean the exact same thing. They're in just different forms. Okay, so same graph. So how do we read this properly? You say y equals, and then see here that I've highlighted, log of x to the base a. Okay, so I know you want to say log ax, that's kind of improper form, so log of x to the base a. So this is the nice y equals version, okay, of this graph here. Just as with exponential functions, with the base here, the base cannot be equal to 1, right? And the base must be greater than 0. Okay? The reason why the base can't be negative, just with exponential, so for example, if you had -2 raised to the 0.5, so say you had it raised to a rational power, that's really the square root of -2. Okay? This produces an answer which is what we call, basically it's not a real root. Okay? So these are called imaginary values. Okay, so when you have a square root of a negative, that's imaginary and it's not a real number. We don't go into that in this course, you don't have to worry. But essentially that is why we cannot make the base negative. Okay? If you're wondering why can the base not equal 1, and that's because if you were to do 1 to the x, then 1 to the x is really meaningless because the x, whatever I put in, if I do 1 raised to it, it's just going to equal 1, okay? And then it's not exponential, right? Y equals 1 is not an exponential function, hence the restriction. Okay. So the big main idea here that I want you to understand is that x equals a to the y and y equals log x to the base a are equivalent. Okay, so mean the same thing. And if you want to think of it, if they are the same, right, if this and this is the same, then you can kind of think of the log version as the exponent, right? Because we said y was up here. So then if y is log a to the x, then that's like subbing this guy up into that exponent. All right, so what does it mean? Okay, so you really have to think to yourself, backtrack and think of this original one. So if I give you log x to the base a, it basically is me saying the answer to this is the exponent that must be applied to the base a to get the value of x. Okay. So for example, if I gave you log 8 to the base 2 equals 3, okay? Why does this make sense? Why is log 8 to the base 2 equal to 3? And it's because you would look at this and say the exponent that must be applied to the base 2 to get an answer of 8 is 3. Right? So you ask yourself, so I kind of do this little wraparound method. Okay, so I say 2 to what will give me the answer here, 8. Okay? So that's kind of what you're thinking in your head. 2 to the what would give me 8. And that's how log works. And we'll practice a bit more then on the other page. The shape of the graph of the log function, we just saw depends on the base. Okay, so we just went over that. So remember, when we had, when a was greater than 1 for log, okay, so this was when the original parent function, the exponential, was a greater than 1, so obviously it was an increasing function. When we took its log function, it looked like this, and it too is an increasing function. When we had an a value that was between 0 and 1, it looked like, in exponential form, it looked like the blue, okay, which was decreasing. And then its inverse function, the log function, was here in red. And we saw that that too was decreasing. Okay, so it's maintained. We saw that the x-axis was the horizontal asymptote for the exponential function. Okay, and then obviously with the switch of x and y, the y-axis became the vertical asymptote for the log function. The y-intercept of the exponential function was always 1. Okay, so you can see that here. All right, it's always through 1. And because x and y switch, the x-intercept of the log function was always 1. So that's a new rule here. So the x-intercept of log is always 1. The domain of the exponential function is always xer, okay? And the range of the log function was yer. Again, we're assuming that these exponential functions are those parent functions with the different bases and not transformed. The range of the exponential function is yer, such that y is greater than 0, and that becomes the restrictions for the domain of log, where x must be greater than 0. All right, so let's get into practicing some examples. It says state the inverse functions of the following in exponential form and in log form. So remember, we're doing what we did up here. So if that's the original, what is its exponential form and its log form for its inverse? So we have f of x equals 5 to the x. So we get y equals 5 to the x. I always kind of write it this way just because it helps students to work with x and y. So the exponential version is just going to be swapping these two. Okay, so our exponential version is just x equals 5 to the y. Our log form is going to look like this. So log is going to be y equals log of x to the base 5. So that 5 is lower. Okay. So log and x should be on the same level, and then the 5 is the subscript. Okay, so notice here that the base of the exponential version becomes the base of log. Okay, so here are some little strategies. Okay, little rules I use that you can use as well. So exponential to log. The base of the exponent, right here, should be the base of log. Okay, so look at that in yellow. Okay, so look at yellow. Okay. And now notice the answer of the exponential version, right? I call this the answer because what to what equals x. The answer of exponential becomes the argument of log. Okay, so that's in green. The argument is the input. So it's basically what we would input into a calculator, right? So log of what? And that's what we would plug in. So following that same rule, let's see if we can come up with this one. So we have y equals 1/2 to the x. So exponential version is easy because we can just swap x and y. So we know the exponential version is x equals 1/2 to the y. The log function, okay, so remember, the base of this version must be the base of log, and the answer for this version must be the argument of log. So we get y equals log of x to the base 1/2. All right, let's turn over. So it says rearrange the log functions into their exponential form. So this is where you can kind of do that wraparound method. So I always do, okay, 6 to the y must equal x. So do that wraparound. So the base to there has to equal the argument. Follow that same method here. That means 2.5 to the y must equal x. So we have just converted from log form to exponential form. All right, let's continue. These ones actually have answers in them, so the statements have already been solved. So it says log of 64 to the base 2 equals 6. So in its exponential form, that's going to be 2 to the 6 is equal to 64. There we go. And that's true. Here, we're going to rearrange this to say 25 to the 1/2 equals 5. That is also true because think about it, 25 to the 1/2 is the same thing as root 25. Root 25 is 5, so 5 equals 5, so that verifies that's correct. Log of 1 to the base 8 equals 0. So that's 8 to the 0 equals 1. Okay, and that's true. Any number to the 0 equals 1 as long as the base isn't 0. Log of 1 over 9 to the base 1/3 is equal to 2. So that would be 1/3 to the 2 equals, okay, so remember doing that wraparound method, 1/3 to the 2 is equal to 1 over 9. And that is true because we'd square the top and bottom, so that'd be 1 squared over 3 squared, which would be 1 over 9. So that's correct. All right, now we're going to use what we know about exponents to evaluate logs. Okay, so up here I gave you the answer for all these logs, and we rearranged it. So now we're going to come up with the answer ourselves. So let's use what we know about rearranging to exponential form, because that might help us. Okay. So we know if I rearrange this, that this is 6 to the y equals 36. So I want you to think to yourself, what exponent 6 to what would equal 36? And you should be thinking that it is 2. So when you square 6, it equals 36, so y equals 2. We just evaluated that log expression. So this is how converting to exponential form is helpful. All right, we've got log 3 to the base 9. Like I said, I always equate it to a letter, so I just equate it to y. You can equate it to x too if you want. So I set it equal to y. I convert it to its exponential form, and then I think about what the answer could be. So its exponential form will be 9 to the y equals 3. So notice here, when you have the number 9 here, and then the answer is smaller than what the base was on this side, that's a hint that the value in your exponent is going to have to be a smaller number between 0 and 1. So we have to think, 9 raised to what would equal 3? So you have to do some thinking out the side here. I know that 9 to the 1/2 is the same thing as square root 9, which is equal to 3. So basically the exponent here that would make left side equal right side would be y equals 1/2. So we just solved log 3 to the base 9 equals 1/2. All right, log of 10,000 to the base 10. So I'm setting it equal to y. I'm going to convert it to its exponential form, 10 to the y equals 10,000. And then I ask myself, 10 raised to what would equal 10,000? And that would be an exponent of 4. So I just evaluated that log expression equals 4. All right, the next example here says find the value of x. Okay. So notice x is in different places for all the parts. Okay. So in this case, x is the answer to log. All right, log 27 to the base 1/3 equals x. All right, so if I convert it to its exponential form, that's 1 over 3 to the x equals 27. So how does a fraction raised to a power equal a number that's much greater than 1 over 3 itself? So in this case here, that means somehow the 3 has to come up to the top. So you have to think to yourself, we know that 3 cubed equals 27. Okay. However, the 3 is at the bottom here, so that would give you 1 over 27. So how do we bring the 27 up to the top? So let's think, what if I raised it to the -3? Then I'd get 1 over 3 to the -3, and then to make it positive, I would bring it up to the top, so it'd be 3 cubed, and that would equal 27. So that means the answer to this question is -3. Okay, that's the only thing that when I plug it in here would give me positive 27. All right, log x to the base 5 equals 3. So now x is the argument. So again, I want you to rearrange to your exponential form. So you're going to get 5 to the 3 equals x. And x is already isolated, so this one's easy. So all we have to do is 5 to the 3. We know that's 125. All right, now we are solving for x as the base of log. Okay, so just a little reminder that bases can't be negative and they cannot equal 1. So let's rearrange this to our exponential form. So that would say x to the 2 equals 1 over 16. So we have x squared equals 1 over 16. We're going to square root both sides. And notice that I'm only doing the plus version. I'm not doing the minus because bases can't be negative. So I'm just going to do the positive square root of 1 over 16. So x equals positive 1 over 4 only. And lastly, here we've got 3 to the 0. If we were to rearrange this, would be 3 to the 0 equals x. And we know in math that any base other than 0 raised to the 0 always equals 1. So here x equals 1. All right, now let's practice writing it in log form. Okay, so we'll do this, write the following in log form. So now we're starting with exponential and we're going in the other direction. So 3 to the 3 equals 27. So remember, the base becomes the base of log, the answer becomes the argument of log. So this is the same thing as log 27 to the base 3 equals 3. Okay, so that exponent there becomes the answer of log. Okay, and that makes sense. Do the wraparound method. 3 to the 3 equals 27. Good. 4 to the 5 equals 1024. So remember, answer becomes argument, base becomes base. So this becomes log 1024 to the base 4 is equal to 5. 2 to the 7 equals 128. So that's going to be log of 128 to the base 2 is equal to 7. And lastly, 1/3 to the x equals 27. Okay, so that means we're going to get that log 27 to the base 1/3 is equal to, and then it should always be equal to the exponent, which is x. Okay. Again, every time you rearrange and going back to exponential form, you should make sure you get this answer back. All right, so we've seen here that we get a lot of different bases for log, 1/3, 2, 4, 3, right? We know it can be anything greater than 0, but not equal to 1. So scientific calculators can perform log operations using the log button, okay? However, okay, so highlight this, the log button, okay, can only be used for base 10. You may have a calculator actually. Some calculators do allow you to change the base of log, but most calculators don't. And so when you're working with the log of base 10, that's the only time you can use the calculator button to solve. So for example here, use your calculator to find the value of each of the following. Okay. So because here, see how the base is 10, okay? That means you're going to type into your calculator right now log of 1000. Okay, the 10 is already automatic. Okay, so you don't have to enter it in. So you're going to do log of 1000, and you should get an answer of 3. Okay. If you are not getting that, then you might want to, work around or get to know your calculator a little bit and maybe see what you have to do to fix to get that answer. Now notice here with the next two that I didn't put a base in, okay? So when no base is given, okay, so when there is no base, okay, it is implied that it is base 10. Okay, so just like with square root, right, with square root we don't put the 2 in there because the 2 is implied. The same thing here. So there's an imaginary base 10 there. So we can enter this into the calculator. So log 50 should be equal to about 1.7. And you should try typing in now log of negative 1000. And you should get error message. And that makes sense, okay? Because when you try to enter that in. So log of negative 1,000, there is no number, if you have a base 10 here, okay, so if I were to convert this to its other form, exponential form, we would do 10 to the y equals negative 10,000, or sorry, negative 1,000. There is no such y that exists, right? There's no positive base that when raised to exponent would give me a negative answer. Okay. So this is how we know that would not exist, and that's why it makes sense. All right, I hope everyone enjoyed learning about 8.1, the log function, and get ready for 8.2. Good luck with the homework.